Hello. In this video, I'd like to talk about how to calculate probabilities using some of the technology that we have available. Let's start with the binomial distribution. Now, for the binomial distribution, we're looking at calculating exactly X number of successes out of N trials for a constant probability of success for each trial. From your textbook, you should recall that the formula for this is the probability of X successes is the number of combinations of N trials taken X number of times the probability of success to the X power times the probability of failure to the N minus X power. Using a Texas Instruments graphing calculator, we can also calculate this same probability using the distributions found by going to second, vars, which gets you the distribution functions, and then from the menu that appears, scrolling down until you get to option 0, which stands for the binomial PDF. If I open up my graphing calculator, you can see that happen. Clicking, turning on my calculator. I want to access the distributions, so second, vars, and from the menu of distributions, you'll see a whole wide variety of distributions. The normal distribution, the t-distribution, the chi-squared distribution. If I use the down arrow to scroll to the binomials, I'm going to want to choose a binomial PDF, which stands for binomial probability distribution function. Now, in order to use this function, we need to know what to type in here. And as you'll recall, the binomial distribution takes a number of arguments. We'll need to know the number of successes we're interested in, the total number of trials, N, the probability of success as well. And those are the arguments for the binomial PDF function in your graphing calculators. If you are using like a TI-84, some of these interfaces will actually prompt you for N, P, and X instead of having you type them in as a comma delimited argument. So if I were interested in the probability of getting exactly 2 successes out of 10 trials for a binomial experiment that has a probability of success of 35%, I can type in the binomial PDF function with the arguments 10 for N, 0.35 for P, the probability of success, and 2 for X. And I'll get the corresponding probability of success, which is approximately 0.1757 if we round to the nearest 10,000ths. Let me bring up that calculator again and type that just to verify. For 10 trials, and then I hit the comma button, a probability of success of 35%, comma, and we're interested in 2 successes. I hit enter, and yeah, I get the probability of success. Now, you can also calculate these probabilities using Excel. In Excel, within the function line here, we can just type equals and binom.dist. So we'll type in the equals, and once you start typing the word binomial, B-I-N-O-M, the code assist will bring up functions that start to match that. And not only will it list the functions, but once you select one, it will give you the arguments that you need. So within an Excel document, if I were to type in equals and start typing in the functions, you'll notice right off the bat, I see the binomial functions that are available. So if I select the first one, B-I-N-O-M for binomial, dot distribution, D-I-S-T, you can see it has the arguments of the function listed here. The number of successes, the number of trials, the probability of success, and then there's a Boolean, true or false value that they want. They want to know if we want the cumulative distribution or the cumulative probabilities or just exactly X successes. We're always going to say we just want exactly X successes. So the value for the cumulative argument will always be false for we do not want the cumulative probabilities, just exactly X number of successes. And that's why I've listed the fourth argument here as a hard-coded false. For example, if we wanted to calculate, again, the probability of exactly 2 successes out of 10 trials, where the probability of success for each trial is 35%, the arguments would be 2 for the number of successes, 10 for the number of trials, a probability of success of 0.35, and once again, false for cumulative. And when we type that in, we'll get the same probability that we saw with the Texas Instruments graphing calculator. So within here, the number of successes, 2, the number of trials, 10, probability of success, 0.35, and then a false for the argument. And you can see, yeah, I get the same probability. Now let's move on to the normal distribution, where we're going to calculate the probability of some value being less than or greater than some other cutoff value. Now you'll recall from table A2 from the normal distribution, which is really the standard normal distribution table, they only give you cumulative areas from the left. So once we've computed the standard score for some value from a normally distributed random variable with a mean and standard deviation, then all of the areas will always be cumulative areas from the left. The way that we can calculate these cumulative areas is to use the standard normal distribution table in the book, or we can use our Texas Instruments graphing calculators, TI-83 or TI-84, and we can also use Excel. Now, using our graphing calculators, and sorry, this is a TI-83, not a TI-84, but the TI-84 is very similar. We'll access the distributions again, and now choose the option 2 for normal CDF, which stands for normal cumulative distribution function, because we aren't going to want exactly one value's probability, but a cumulative area from the left. The arguments of the normal CDF function is to specify a left cutoff value, a right cutoff value, a mean, and standard deviation. Now, let me go back. When we talk about a left cutoff value and a right cutoff value, we're asking for the values of z that we want to calculate the area above and below the normal density function. So in this case, when we're talking about just a single z-score and the cumulative area from the left, we're talking about a right cutoff value. And the left cutoff value doesn't exist because we want the total area, to negative infinity, up to an upper bounds or upper cutoff or a right cutoff value of what we specify, z. So in that case, when we specify the left cutoff value for the normal CDF, we're going to use a value of negative, meaning the negative button down here on our calculator, not the minus sign. That's an operation. That's subtraction, which we're not doing here. But we want the minus sign that looks like this on our calculators, followed by EE, which is the secondary function above the comma, second comma, and then typing in the numbers 99. Negative E99 is scientific notation for negative 1 times 10 to the 99th power. So it's negative 1 with 99 zeros after it, a very, very small number. If we did want to calculate a cumulative area from the right, we could use a positive infinity for the right cutoff value. And we would use for a positive infinity just a regular E99 instead of the negative E99. So in this case, if we want to calculate the cumulative area from the left of a z-score of 0.75 for the standard normal distribution, and as you recall, the standard normal distribution has a mean of 0 and a standard deviation of 1, then the arguments of the normal CDF would be negative E99, because the lower bounds doesn't exist. It goes on to negative infinity, all the way up to a z-score or a right cutoff value of 0.75 with a mean of 0 for a standard normal distribution and a standard deviation of 1. Now, you'll notice that if we're specifying the mean and standard deviation, we could use this normal CDF for any normal distribution given its mean and standard deviation, not necessarily 0 and 1. But I'm doing it for this example just to verify, using table 8.2 that we get the same thing. So, breaking out our calculator again, I go to distributions using second vars. I select my normal CDF, specify that the lower bounds is negative infinity, comma, my upper bounds or right cutoff value is a 0.75, my mean of the standard normal distribution is 0, and the standard deviation is 1. When I hit enter, I get a probability of 0.7734 approximately. You can verify that using the standard normal distribution for a z-score of 0.75. You can see the probability is in fact 0.7734. Now, we can also use Excel to calculate our normal distribution's cumulative area from the left. And this is going to be using the function norm for normal dot distribution. And the arguments will be the right cutoff value, the mean of your distribution, the standard deviation of your distribution, and this argument for cumulative. Now, because we do want the cumulative area from the left, we are going to specify a value of true for this argument asking for the, whether or not we want the cumulative area or not. Everything else is going to be nearly identical to what we did with the graphing calculator. So for a cumulative area from the left, for a z-score of 0.75, which is to say the probability that our z-score is less than 0.75, I can use the normal function dot distribution, parentheses 0.75, for the right cutoff value, comma 0, comma 1, and by specifying true, it will always give me the cumulative area from the left. So if I break out Excel, you can see there is a limitation now with this normal distribution, this function. So if I start typing in normal, you can see it code assist and gives me all the available normal distributions. I'm going to choose the norm.distribution or norm.dist. When I select that, you can see the code assist. So this value of x, the cutoff value, for this function, it is always the right cutoff value. So 0.75. The mean for a standard normal distribution was 0. The standard deviation was 1. And then for the cumulative indicator, we do want the cumulative area from the left. Now, if we wanted the cumulative area from the right, then we could just use the complement rule. So that's the reason why Excel is doing this. And you can see that, yes, we do get, in fact, the same area, 0.773373 approximately. You can see that in the slide as well. And that concludes this video.